guys. So that was entertaining. We'll see how this goes. It turns out that the all my past year's machinery is kind of not working because the projector doesn't support 1024 by 768. But anyway, I'll figure that out. So if today's a little weird, it's a little weird. So you know, I never was in President Nikias' office before. It's one of the fancier places I've been in, and you might think I have a fancy office because I have a Buzz Lightyear, but he beats me. Well, let's see. So you guys are sort of filling up the room. There was supposed to be a room for 50 people in the class, and last I checked there were 37 of you, but things are kind of full. So we may do something special on exams. I don't really know, because on when we do midterms and finals, we're supposed to be in a room such that you guys aren't packed, your elbows are not actually overlapping, but we'll see how that goes. Okay, so to begin with, let me figure out the thing about the class website and how this stuff works. So right now, this is just the regular astronautics website, and this is what the world sees. If you click this sign on thing, then it will proffer you to well, it should. What's going on with my net connection? Oh, look, it thinks I have no net connection. How cool. Well, we will, oh, you know what? Let's see if it has a wired connection. Okay, we'll see if that sorts out the wired connection in a second. My hope is to actually log into the, hey, reset the network. My hope is to actually log into the website and show you what's going on. So, okay, that's a net connection. Good. So I'm going to log in as me, which is of course different than when I log on as you. But when you're logged in, notice it says you're signed on as something. First of all, the website is not smart. It's not shibboleth, so it doesn't use your USC password. You have your USC username, but you have your own kind of random password, which you can actually change on this website. And you guys got my email yesterday, right? Good. So you can, there was, when you were signed off, there was a link that, well, let me just sign off and show you. There was, when you go to sign on, there's a thing that says email password, and it will send you a password. And then once you have that, you can actually log in. Of course, it remembers mine because it's my machine. So once you are logged in, it knows you're enrolled. There's a bunch of links here that are my links, so you won't see them, but you will see a link that goes to the course webpage. And once you go to the course website, you see a bunch of stuff that's specific to you being logged in. You see the homework assignments. There isn't one yet. You see the lectures. These are, we will see how this works. I'm trying to record at a different resolution now, so it may not happen for today. We'll see what happens. But normally, the lectures, the PDF of the lecture slides are going to be here, and also the videos of what actually appears on the screen. So they're kind of dull. They're just the screen and my voice, and kind of a muffled version if you guys ask questions. Basically, it's a recording of what happens in the room and on the screen. And it's handy in case you forget what happened in class. You can go back and look. Occasionally, if you just miss class, and by the way, I'm not going to take attendance. If you miss class, you miss class. You don't have to apologize or anything to me. You guys are, grown-ups. You can manage your own time. If you miss all the classes, you're likely, statistically speaking, to do poorly on the exams. But so the one thing that's on here, the syllabus. Once you're logged in, the syllabus is hidden at a separate link, and it gives the catalog description. And by the way, you're supposed to have had a couple of prerequisites, and you're supposed to be good at MATLAB. Notice the recommended preparation. So what occasionally happens is some people will come and take this like from physics or from some major where they don't tend to use MATLAB, and in that case I recommend that you do kind of a fast catch-up and come and see me. I will give you some slack on the first few homework assignments if you haven't done MATLAB before. But there will be, so make sure to let me know so that you're not exposed to the full force of having to do everything. Because when you're brand new to MATLAB, it's kind of a painful learning curve, as most of you guys know. So normally this is taken at the end of the sophomore year for both Astros and Aeros. It's a required course. A few of you guys are probably not from those majors and are taking it as an elective. Here's basically what you're supposed to learn. There's a bunch of topics. The thing we're going to work on today, actually the first couple of weeks, is coordinate systems, coordinate transformations, how to describe where you are and what direction you're going, which is preparatory for understanding things like orbits and attitude dynamics and things that are primarily 3D. So there's a lot of things in this class that are, because this is about space and what we do in space, there are a lot of things which are complicated to visualize and draw pictures of and describe, and everything's 3D. So we're going to be pretty good at understanding different coordinate systems and how to transform between them. The coordinate systems may move with the Earth, they may be centered at the sun, they may turn, they may not. We may work with spherical polar, we'll work with all these different kinds of things and show where all the transformations come from. And some of the stuff you will have seen before, but we will have kind of put it on a little firmer level, I think. We'll do orbits, not just orbits, but transformations between orbits, or that is maneuvers where you're in one orbit and you go to another orbit. And there will be both Earth and interplanetary trajectories. We will look at rocket propulsion in different kinds. We will look at rigid body rotations and maneuvers that involve orientations of a spacecraft, because spacecraft have to be able to move. They also have to be able to turn and point. And there's some math there and some physics that you probably will not have seen unless you've already taken AME 301, which is dynamics. If you've already taken that, this section will be easier. On the other hand, if you take 301 later, then having been through this will make that part of it easier. There's a bunch of stuff that you do in the engineering curriculum where you don't really get it the first time through. You have to get it like the second or the third, sometimes the fourth time through, and that's perfectly okay. It's normal. There's a few weirdo people that get things the first time, but they're kind of outliers, and most of you aren't like that. I wasn't like that. There are a lot of things that I didn't get until the fifth or sixth time through. But the flip side is, I know them really well now, and I haven't been in school for many, many years, but I know all the stuff really well. The people who, this is, for most of you, this will make you feel better. The people who understand stuff the first try, usually it goes into kind of a short-term part of their brain, and they get it kind of fluently, but they don't really keep it. If you have to work for something, you keep it better, and it becomes part of you. So feel better if stuff happens in here that you don't quite get, and you later get it in other courses. Of course, there are possibilities. I don't explain stuff too well, but we'll see. So now I need to discuss grading and textbooks. There's no required textbook. I will be posting PDF notes and chapter 1 is already posted on the website. I don't know if you guys downloaded it. There are a couple of recommended texts. One is this thing, SMAD, Space Mission Engineering, the new SMAD, which is a big red and white book, and it's not a very good textbook for learning things out of, but it's a really good reference book. So if any of you guys are planning to be in the space industry later, and I know a lot of you guys are Aeros and you're just taking this because it's a required course, you're not really interested in space, which is fine, I understand that. Some of you are kind of astro in your head, but you're an Aero, so you're like closet astros, that's okay too. What occasionally happens after people take this class, sometimes they take it and they think, oh God, I'm glad I'm not an astro. Other people take it and they think, actually space is kind of cool, and they start to kind of track and take astro electives and stuff. And so the course sometimes causes people to switch out of astro, sometimes it causes people to switch into astro, whatever. But if you think you're going to be in the space industry later, having SMAD as a reference book is a really good idea, because it's a big, thick book. Again, it's not very good for learning out of, but it's really good for finding formulas in, looking for examples, finding out what people really do, and short descriptions of why, but it's not so much why. The second thing, Francis J. Hale, Introduction to Spaceflight, that's an actual textbook. That explains things. And the only reason I don't have it as a required book is it's expensive. You look at the thing, it's a paperback, but last I checked, it was like $95. And if for some reason textbooks are free for you, yeah, go ahead and do it. But if you're spending your own money or your parents' money, maybe you don't need to get it. it is always good to have a reference book that explains things differently than what the instructor does. Because, I'm giving you my course notes. It's probably going to explain it kind of like the way I do, you know what I mean? But if stuff's hard, and some of the stuff in this class is hard, it's a good idea to find some different explanation, whether it's just Wikipedia, or another textbook, and they will explain it differently. And you think, oh, is that what the dude was saying? Okay, fine. But you don't have to buy anything. You can just use the PDF notes that are posted here. We are going to have 2 midterm exams and a final exam, so it's pretty straight up that way. There's going to be homework due every week, not this week, but starting a week from Thursday. First assignment's going to be done. So homework is 20% of your grade. The midterms are also 20%, so that makes 20, 20, 20, that makes 60. Final exam is 35, that makes 95. I've left class, there's a class participation thing, which is 5%. And I did this for the first time last year at the recommendation of a lady named Gigi Ragusa, she was in the School of Engineering. Now she's completely in the School of Engineering, but she's an education professional, and she's one of these people who kind of knows how to take difficult stuff and provide mechanisms for enhanced learning. So this is not an attendance thing. You don't get class participation just for showing up. What the class participation is a thing where a few times during the semester I will ask you to get in groups. I will ask you to get with a few people in a group and talk about something and make a short presentation about it. And it'll just be stuff. It'll be material that's related to what we've covered in class. It's not like a big research project or anything. And so you will be asked to stand in the front of the room and present with your group. And we did this last year, and it was kind of interesting. One of the things I found was that the things I asked the groups to do, mostly they didn't get, and so it was a sort of feedback for me as to what you guys are getting and what you aren't. And so I'm going to be able to zero in on that a little better this year. Mostly I think people had an okay time doing it, but again, it's still experimental from my point of view, and if there's a screw up, I'll just give you all 5% of A on it, so you don't worry that just because if it goes poorly, I will take it as my fault, not your fault. So, and actually, on the exams, I'm not exactly a grade on the curve kind of guy, so that I'm not going to grade for an average grade of B- or whatever. But on the other hand, so normally I can kind of tell how you guys are going to do on exams or how you should do. So, but on the other hand, if sometimes I give an exam that's extra hard and everybody gets low scores on it, and I don't penalize the whole group for that. If the whole class does poorly, I figure it's my fault and not your fault. So in that sense, I do grade on a curve, but I don't. So it's sort of it's my own kind of hybrid grading way. By the way, your homeworks are going to be graded probably by a TA or a grader, but the exams I'm going to grade. So. I will, if I don't see your stuff until week 5 or 6 or whenever the first midterm is. And by the way, schedule is down below. And so here's the actual dates. You see, of course, everything is Tuesday and Thursday for each of the weeks. First midterm exam is on February 19th. Somewhere down here we have spring break, and then second midterm exam in week 11, and then finally at the very end we do some final stuff, we review, and then there's a final exam. And as on every syllabus, you're supposed to pay attention to a thing about academic conduct. You guys, I'm sure, have run into this in other classes, but the university mandates fairly strict penalties on plagiarism. And in this class, I'm not asking you to do any big projects. I will ask you to take exams, and I will be kind of watching you while you take the exams, and I will be. When I grade the exams, every once in a while, I notice something that's kind of suspicious, like very similar to something somebody else has written, and I look at the photos that I've taken during the exam, and I find out, aha, they were in fact sitting right next to. You know what I mean? So I do pay attention, and my assumption is that you guys don't do that kind of stuff, but I am obligated by the university to look out for it. So please don't consider it personal. It's not like we're required to do it, and it does happen sometimes. As far as homework goes. I expect you guys are going to collaborate completely and work together like students always do, which is fine. I do expect you to turn in your own work, and there are going to be some programming problems in here. Remember, I said MATLAB was important, and some of the assignments actually are going to be largely MATLAB, and it's a temptation to kind of figure out in a group how it does and then just share the file. Please don't do that. It's not like you're going to have to do huge programs which are pages and pages anyway. I'm not going to make you do that kind of stuff. So please, even though you get something working in a group, please do stuff on your own before you turn it in. There is also a statement, it's on every syllabus of every class, as to the kind of support that you may need in case you need like extra time on exams or that kind of thing. If English is not your first language, it's probably a good idea for you to come and see me and let me know, particularly if it makes it some difficulty in class. If there may be some emergency that happens during the semester, in which case everybody works from home and you'll get some kind of announcement. Nobody knows how, but there will be something will happen that will indicate that we will try to keep classes going even though we're all at home, and presumably it'll be some kind of internet-related deal. Now, the final thing I'm going to say about the boilerplate is, I didn't put it in writing yet because it's not scheduled, but I kind of think I'm going to have a little bit of surgery during the semester I have a deviated septum and I hope to get it straightened, and that will take me out of commission for about a week. So what'll happen is I will pre-record a couple of lectures and let you know with some time in advance. I'll give you plenty of warning. And what'll happen that week is basically it'll be just like any other week, except you won't come here. The lectures will be posted online and you'll download them and look at them. You can sit in a room and talk and throw spit wads at the front of I don't care, whatever you want to do. But I will not be here. What that means, of course, is that whatever weirdness is going on with my recording of videos, I have to have figured out by then. Okay, any questions on sort of the boilerplate of the class, the basic bones of how it works? Let me show you a couple more things about this, about the website. If you go back to the place where where you're logged in on the website, there's some links here. The picture directory is more for me than it is for you guys. I intend at some point to. Here's everybody. I intend at some point to know everybody's names. I know a lot of you already, but I don't by any means know everybody. Actually, on my, I usually write a little bit of scripting so that will flash unnamed pictures in front of me, and I have to spit back your name. Hey, okay, we have to do it somehow.
That's dedication.
Well, actually, I'll tell you what the problem is. A lot of these, most of these pictures are just like the pictures you guys sent in. You recognize them as your roster pictures, right? So some of them are still in high school. You're wearing your tuxes or whatever. That's cool. One of you wore a tux for your picture. That's cool. Now, so I can't tell just from they're just headshots. I can't tell, I look at some picture of some smiling freshman, and then I see them, and in person they're like 6'3", you know what I mean? Or just I don't get a sense of what's really going on until I actually see you guys. So if I have trouble actually learning who everybody is, I'll resort to a thing I used to do where I give out name tags and kind of videotape the room, and then I can kind of see, I can kind of actually see what everybody looks like in person, tall, short, whatever it might be. So, but one way or another, we'll get it done. Let's see, when I send the email to a class, which I've done one of already, it shows up in the announcements. So this is the email that I sent you yesterday, and it says the date and time that it was sent. It says who sent it, which is typically going to be me. And so if you delete the emails that I send you, that's okay, because they're present here on the website. And this is blog style, so the latest one is going to be first, and this email is going to be later on, way down at the bottom. Okay. And let's see, there's once you have a little graded work, there's a thing where you show the grades. I think nothing will appear right now. Oh, you are not a student. Well, all right, fine. It's true, I'm not a student. Okay, but you guys are students, and at some point it's kind of bare bones, but it'll show you what your graded scores are. So. One of the things that's handy for is if you get back an assignment and you say, oh, there's some problem grading, and you come and talk to me and I fix it, you can actually check later on to see that it actually did get fixed. And if it didn't, you can bug me, and we can. I have, by the way, one general piece of advice for you guys that applies to your entire careers, basically, is whenever you do something that's not quite in accord with the rules, you petition for something special, or somebody gives you permission to do something unusual, get it in writing. Particularly if it relates to your transcript or some of your requirements or something, because what can happen, and I've known this to happen on a bunch of occasions, I've been doing this a long time, you talk to some professor and they'll say, oh sure, we'll do it this way, no problem. And then the guy goes on leave or sabbatical or retires or has a car accident, and then you're stuck because nobody has any record of it. So what you always do is you get it in writing, or if it's an email, you keep the email and you copy it to some other server or something, and you guys know about backing up and keeping copies, right? I mean, they say that stuff lasts forever, but the flip side of it is stuff doesn't last forever. The stuff you want to keep doesn't last forever. The stuff you don't ever want to see does last forever. So, in particular, if you're told that you will be able to substitute one course for another, or something along those lines, always get that in writing and make sure it appears on your STARS report. I will show you some more things you can do with the website. If you go home, well, I can turn in any of you, which I won't do. You can edit your personal stuff. There's some stuff related to faculty, which you won't have. You can change your password, which it does the obvious thing. You can upload different pictures. I have some old pictures of me from years ago. Let's see. Oh, I have no backlink. You can add additional email addresses. So if for example you like to use a Gmail address and then you can put it here in addition to your regular USC one, and then any email that I send will also go off to the Gmail one. So that is handy. I think that's as much as I want to say about that. Okay, so now I'm going to actually now I'm going to look at the actual course material. So we're doing the very beginning of this math, which is basically about coordinates. And why do we have coordinates? To specify where we are. And by the way, if you find it helps you to take notes, by all means take notes. You don't have to, in the sense that first of all these notes in printable form, like textbook form with the equations and everything, are downloadable as the big PDFs. There's one there already. And also these slides, if I will publish the slides that I present here too, and if I write on them, and my pen there's a funny offset, so my writing is going to look a little spazzed. So all this stuff I'm going to publish after each class, so you can consider taking notes to be optional if you want to. So the first thing we'll look at is just is units, because in when you graph things in math, it's just numbers, right? They say go from -1 to 1 or whatever. -1 to 1 what? Well, in this case, we're always working on some length scale. If we're in the solar system, our length scale might be astronomical units, the distance from the Earth to the Sun. Or we might be working in kilometers, in which case the natural length scale is like 100 million kilometers. If we're working around a spacecraft, the natural length scale is like 1 meter, or even tens of centimeters. If we're working interstellar space, which mostly we don't do, we have only a couple of spacecraft that have even left the solar system, let alone gone to other stars. But astronomers, of course, work in longer length scales, and we'll talk about those briefly. Coordinate systems, I mentioned several different kinds. There's if you just draw axes in math, well, that doesn't really give you much information. In our case, we're always working in the real world, so our coordinate axes are going to always have an origin, which is some particular place. Center of the Earth, center of the Sun are the two most common places. And whether or not they rotate or whether they're fixed, meaning they point off into inertial space and the directions are always the same, that's a couple of other ways they could change. So we'll look at all stuff like that. There's a subject called spherical trigonometry, which is like plane trigonometry, except it's triangles on the surface of a sphere. And this is a thing that is, it used to be taught as part of navigation on sailing ships, because sea captains had to know it. It was how you navigate. And, the whole thing that happened in the 1400s and 1500s when people decided that they could actually sail these little wooden things all around the world, they learned all kinds of math to help them do that. And it turns out that math for navigation is also the same math as you need when when you're talking about orbits and how orbits intersect and how you transfer from one to another. Spherical trig comes in all over the place. So that will be one of the subjects, and we'll actually start on that today if we get that far. Rotations and rotation matrices are a set of math for transforming from one coordinate system to another. And an example of the kind of thing that we'll be able to know how to do when we're done is if, let's say that we figure out where a planet actually is at this moment in the solar system, and we know where Earth is at this moment in the solar system. Now, if you want to know where to actually see that planet in the sky at 8 o'clock tonight, if you're in Los Angeles, where do I look? Is it even visible? Well, that's a fairly complicated example of a problem that requires this kind of math. And so that will in fact be the sort of a culminating problem at the end of this section. I'll show you how to do all that. And so just to give a very quick flavor, if we have the sun and the Earth somewhere and this other planet that you're trying to find some other place, then these are physical locations. And so we're going to have to know how to change the origin from the Earth to the sun to the other planet if we want to do it that way, or maybe the other way around. And then we got to do the rotational stuff because the Earth is pointed off in some funny direction. You know, the spin axis of the Earth is at some weirdo angle, which gives rise to seasons. We'll talk about that. And furthermore, where the Earth is with respect to the time of day, that's a rotation that we need to figure out, and where it is in respect to the time of year. All these things come into it. And when we're all done, we should be able to say, okay, we go to an azimuth, which is you start from north and you go around and you say, okay, I'm 70 degrees from north, and then my elevation is 32, and bang, there's Saturn. Okay, that's the kind of thing that this thing will. That's one example, but we'll see all kinds of applications for this stuff. Polar and Cartesian, well, I think you've seen it before, but we'll have it in a number of different ways. One of the things that we'll use actually rotation matrices for is to prove and show where the spherical trig stuff comes from and how to actually prove everything. We will look at coordinate transformations in a sort of a generalized way where we consider rotations and translations, all, which means moving, all in a kind of a unified approach, which, by the way, is the same approach as is used in computer graphics. So it always happens that some fraction of people with engineering majors decide, you know what, I don't want to just play video games, I want to actually go and program video games and go off and be a game programmer. And this is all the same math. So if you get kind of good at this stuff and good at 3D physics and the math that describes it, well, then you'll be one step up to being a games person, if that's what you decide you want to do. One of the things that we need that is important for describing a spacecraft, or a planet for that matter, you want to know not just where it is, but how it's oriented. And so if you consider something as just a point, how it's oriented doesn't matter, because a point can twist and turn, it's just a point. But a spacecraft or a planet has a particular orientation in space, or an aircraft for that matter. You guys are aeros, you know what roll, pitch, yaw means. So we will look at exactly, from a mathematical point of view, what roll, pitch, yaw means, and how to actually express the orientation of something that has a specific set of roll, pitch, yaw angles. And it could be a spacecraft, it could be an ocean-going ship, it could be an aircraft. Typically you use all the same math for describing the orientation. Now, in addition to roll, pitch, yaw, we use a different set of angles which are called Euler angles, and we'll talk about those as well. And it turns out that Euler angles we use for describing the orientations of orbits. So we will discover how to transform back and forth between one set of angles and another. Now, for you astro majors, one of the courses that you're going to take later on as a required course is spacecraft attitude dynamics, which is ASTE 480, and you take that in your senior year. And one of the things they do in there is they talk about how to represent orientations and how a spacecraft is turning and the torques and all the kind of thing that affect a spacecraft orientation. And they express them in this funny four-dimensional thing that you probably haven't seen called quaternions. And we will actually touch upon that in here. We won't do a whole lot with them, but it's kind of an interesting thing because quaternions were a thing that were invented actually in the 1700s, but no one saw any good really use for them. But now, suddenly, many years later, mathematicians and physicists and engineers are finding all kinds of cool use for them. So there's all sorts of things that are suddenly blossoming and taking on new life if you reformulate them in quaternions. And one of the things turns out to be attitude control. And the reason is, if you just describe roll, pitch, yaw, if you describe orientation with roll, pitch, yaw, it turns out that isn't quite sufficient in all cases, or it's not unique in all cases. So, for example, if you have an aircraft attitude, if it's roll, pitch, yaw, 0, then it's straight and level flight. Well, that's all good. But if you pull the stick back and you have the nose straight up, now it turns out that the roll and the yaw turn out to be kind of the same thing. So what that actually means is, for those specific kinds of orientations, the description is what mathematicians call singular. And when you write a control system that controls the roll, pitch, yaw, if it happens to be near one of those orientations, then what you find is the rotation rates, the yaw rate goes to plus infinity and the roll rate goes to minus infinity, and it basically screws up royally. So if you use quaternions, that all magically goes away. Anyway, we'll talk about that later. Okay, so that is what we will be doing. Let's look now at what we're going to actually do. Okay, so how do we specify locations? And remember, this is all 3 dimensions, so there's the only place in location that we would specify as 2D if we're on the surface of the Earth. You can say if we're at 0 altitude, then we only need 2 numbers to say where we are, which is, we can do it as latitude and longitude. I could do it for small scales. I could say, okay, I'm so many feet from this table that way and so many feet that way, and I could give the 2D coordinates of each of you guys in the room. If we were in a gravity-free environment, some of you would be up there, you'd be kind of all over the room, and I'd have to give 3 numbers for each of you. In general, for things that are in orbit or are traveling through space, we need to give 3 numbers to say where they are. If it's interplanetary space, usually we give numbers with respect to a sun-fixed set of axes. So we will express things either as an x, y, z, which is Cartesian, or as a spherical polar. And actually, latitude and longitude is one example of a polar coordinate system. And we will be doing a fair amount with locations on the Earth's surface, and so we'll be using latitude and longitude to describe those. And I mentioned that a lot of what we do has to do with spacecraft that are orbiting Earth, because the big piece of the space industry, the biggest piece of the space industry involves orbiting Earth spacecraft for doing some mission that involves people, whether it's the GPS spacecraft that run all our GPS devices or allow them all to function, whether it's communication spacecraft that broadcast all our TV signals to dish antennas on people's roofs, whether it's military spacecraft that photograph license plates and do infrared pictures of people charging into buildings. They don't really do that. That's just James Bond. Well, I don't think they do, but I don't have that kind of clearance to really know. I kind of know what I think the limits are of today's surveillance technology, but maybe they've gone a little past it. And actually, there was a famous photograph. Maybe you guys have seen it. There's a bunch of sort of test lettering and test patterns on the ground around the world at various places, which are used for calibrating satellite photography. And there was one famous place where, I think it's in the U.S., but I forget. Anyway, it's U.S. people who put it there, that put like 1 meter high letters at the end of some runway, I think somewhere, I forget. Anyway, you could read it from space, and what it said was, if you can read this, you're where we were 10 years ago. Anyway, I thought that was pretty funny. So anyway, military surveillance is one big application of Earth orbits. A whole lot is done with respect to spacecraft, which all they ever do is orbit Earth in various ways. So we'll spend a lot of our orbital time talking about just Earth. The interplanetary stuff doesn't have any civilian applications, at least that we know about, nor do I know about any military applications. It does have, of course, scientific applications. So the biggest interplanetary spacecraft application is scientific missions that go to other planets. And we'll talk about how those things work and how we actually go from one planet to another. Now, it may happen, and it will happen, that we will have to express coordinates in multiple ways. So, for example, if we're leaving Earth on our way to some other planet, then we're handing off from an Earth-fixed coordinate system to the Sun-fixed coordinate system. So that means we're going to have to transform from one set to another. So that is, remember I said we're going to use matrices and rotational matrix transforms, and this is what we need to, this is what we use them for, or that's one of the things we'll use them for. So, okay, first thing about is length scales. So if we're talking about a spacecraft, things on the spacecraft, things near the spacecraft, how far away the solar arrays go, where the big dish antenna is, the length scale is just meters or maybe centimeters. So for example, the microsatellite group out of the Astro department, which is anchored at ISI, which is over in Marina del Rey, they have launched a couple of 3U CubeSats, and those are things which are about the size of a loaf of bread, 10 by 10 by 30 centimeters. And the latest one that they sent up has a deployable dish antenna, which has a diameter about like this, kind of a small umbrella. So the length scale there is, well, centimeters. But for big spacecraft, the big multi-billion-dollar communication spacecraft, which are in geostationary orbit, those are typically a couple of meters across or maybe a little bigger, and they have deployable solar arrays which unfold, and they may be like 30 feet across, which is like 10 meters. So length scales there is, 1 to a few, maybe up to at most tens of meters. And if we're talking about something big like the space shuttle or the ISS, International Space Station, which is even bigger, then we may be up into the hundreds of meters. Okay. Now, the next length scale up from that is the thickness of Earth's atmosphere, which is also the kind of length scale for distances around orbits, because in order to orbit, you have to be at an altitude of, well, if you want to stay in orbit, maybe a couple of 100 kilometers or higher. If you're in orbit at a couple of 100 kilometers, eventually the air drag will bring you down. So if you want to stay in orbit essentially permanently, you have to be up like 400, 500, 600 kilometers or higher. But to begin with, you have to get through the thick part of the atmosphere, which you typically do with vertically launched rocket vehicles. So we will talk later on in the course about space launches, and one of the things about space launches is the vehicles end up going horizontally because they end up putting spacecraft in orbits which are basically horizontal. But you always want to climb out of the atmosphere as quickly as possible. If we did not have an atmosphere here on Earth, if we were, some different kind of life form that didn't need atmosphere, we wouldn't have vertical launch vehicles. We would have horizontal launch vehicles. We would launch tangent to the surface of the Earth. We would utilize Earth's rotation. And actually, we still utilize Earth's rotation even though we launch vertically because the whole atmosphere is moving with Earth. And you guys may not think about it this way, but we're actually moving west to east right now at 700 miles an hour, something like that. Luckily, the air is moving with us because otherwise it would be a 700 mile an hour wind, which would be really bad. But luckily the atmosphere is fixed. So if you launch straight up from the Earth's surface, if you view this from the rotating frame, because of course Earth is rotating, the spacecraft, the whole launch site is moving west to east with Earth's rotation. So even though you're launching straight up, you still have this component of something like, it depends on latitude of course, 700 miles an hour east, which is added to the velocity vector of launching. But if you, the vertical part of it is actually wasted as far as getting to orbit. All it does is gain altitude, but what you really want is to gain kinetic energy in the orbital direction. So at some point when you've gone up and out of a lot of the atmosphere, you kind of turn. So rocket vehicles have to actually be able to steer. They're not aircraft, but they have to be able to steer. So you go downrange, and then eventually they send something off in a horizontal direction, and they go on elliptical trajectories up to where they finally get into orbit. So how much of the atmosphere do you have to get through? Well, 100 kilometers is considered to be the boundary of space, but it isn't really. You have to be higher up than that to really orbit for more than a couple of hours at a time. Okay. Next length scale up is Earth's radius. And in this country, we usually use miles in elementary school, and so you learn that the circumference is 25,000 miles, and the radius is 8,000 miles, diameter is 8,000, radius is like 4,000. So very roughly speaking, you multiply miles by 1.6 to get kilometers. So roughly speaking, Earth's radius is like 6,400 kilometers. Now you notice I give two different numbers here. there's the equatorial radius, and that's the one we'll be using the most often, 6378. The polar radius is just a little smaller, 6357. So what that means is, if I draw a picture of the Earth, and I'm going to exaggerate, it's if this is, oh, my pen is doing weird stuff because it has to map to the resolution, which is currently wrong. I need to fix that. So if this is the northern direction, and then the equator is this line here. Well, I've drawn it as being heavily spread out like a disk on the equator. That's way an exaggeration. The radius from here to here is this 6378, and the radius from here to the pole is 6357. So they're actually pretty close. But Earth is spread out basically because it's spinning. It's spread out due to centrifugal force. And in fact, well, the Earth is sort of rigid, but it's not that rigid. It's molten in the core. At least that's what we think. Nobody's been down there. There's some weird stuff about Earth's core, which some of the stuff we know everything only indirectly. We extrapolate temperature to the Earth's core because we start drilling down into the Earth, it gets hotter and hotter. We observe that molten stuff comes out from below, so it must be molten down there. We observe that there's a magnetic field on the outside, so there must be some magnetism on the inside, but it's too hot for permanent magnets, so there must be electrical currents. That's all very weird. So where do electrical currents come from in a hunk of rock? Who knows? So there's some weird stuff. Right? And it flips sometimes. The magnetic field, the North Pole is like this. Sometimes the magnetic field points in quite different direction. And actually it drifts around quite a bit. If you were a Boy Scout or some kind of group that tends to camp and learn where you are in the wild, well, these days, of course, people carry GPS units, but still it's practical to have a compass in case your GPS fails. And the compass, of course, points to magnetic north. Well, you have to know where magnetic north actually is. It's not the same as true north. And so you have to know where the Earth's magnetic field is. We will talk about this at the very end of the course. I didn't put it in the syllabus, but I mean in the learning outcomes, but we will actually talk some about the space environment. And for astro majors, you actually encounter more of the space environment in the follow-on course, which is ASTE 330, which is kind of a spacecraft systems course, but the environment is in there too, and in a fairly gory detail. And if you are an astro major, you'll take that as a required course. If you're an aero major, you can take that as an elective. So particularly if you're one of these closet astros that will just sort of shadow the astro sequence, you can take it as a tech elective. So the location of Earth's magnetic pole actually kind of shifts around. It has an angle with respect to the spin axis, and it moves. And from old fossil records, they can tell that the magnetic field lines have been completely different places in millions of years ago. And again, nobody knows particularly how that happens. So, actually, the last thing I was going to say about that was if you do a calculation of Earth's spin centrifugal force and how it should actually be bulged at the equator, and you assume it has no rigidity at all, like it's made of water, like it's a ball of water, you get actually approximately this ratio. 6378 to 6357, slightly bulged at the equator. So the Earth kind of acts like a liquid ball that way. And by the way, because of that bulge, Earth does not act like a point source gravitationally, and that turns out to be important for, it has some things that are good, some things that are bad, but anyway, you have to take into account. One of the things you probably learned in physics, we will look, of course, at the gravitational law in great detail because it's central to much of what we do. But one of the things that they teach you in physics is you take the distance from the center of a spherical source, and which is going to be out here someplace, the distance from some orbital place to the center of the Earth, you square it and you put it in the denominator, and there's something you multiply by in the numerator, which has the Earth mass and gravitational constant. And all that together is the gravitational acceleration. Now, the 1/r squared thing, where it just depends on distance, that assumes that it's either a point source or it's spherically symmetric, which works out to be the same thing. And they probably proved for you in Physics 153 that if you have a spherically symmetric source, like a spherical shell, that the gravity acts like it comes from the center. If you're on the outside, if you're on the inside, there's no gravity. So, there's some interesting math about these things called Dyson spheres, which you may have read about in your science fiction background if you have one. Um, Now, but however, the Earth is not spherical. It's bulged out at the equator, which means that if say you're a spacecraft out here, well, you don't just see the mass as being concentrated here in the center. You see it effectively like spread out like a donut. This part is closer, this part is further away. The part that's closer has a bigger effect because it's 1/r². And so, in effect, the gravity is stronger here because of Earth's oblateness. And at other places, the gravity it doesn't quite point to the center. It points in slightly different directions. So because of that, when we solve the equations of motion, if it's a point source, we get elegant solutions. We get ellipses, we get hyperbolas, we get parabolas, we get circles. None of that stuff happens for an oblate Earth. Things are much more complicated. It's sort of as if they're ellipses, but the ellipses themselves kind of precess over time. And we will kind of work at that level. So these so-called orbital perturbations turn out to be quite important. Okay. Now the last length scale I want to look at is interstellar, and that's sort of for culture because we don't do interstellar stuff currently in engineering. It's stuff astronomers and astrophysics work on a length scale of light years. Now, one weird thing about this is the light year is, well, it's just the distance light travels in a year. So here's the speed of light. And by the way, you may remember it is 3 times 10 to the 8 meters per second. This is the same thing except it's in kilometers per second, so it's 10 to the 5th instead of 10 to the 8th. I will mostly work in kilometers in this course because most of what we do relates to orbits, and kilometers are kind of the natural units. And so all the numbers I give you are in kilometers. And now, you can do things any way you want. You can, in the propulsion industry, they tend to use pounds for thrust. They tend to use feet for nozzle diameters. You can do things in any units you want. Astronomers, physicists tend to work in SI units, which means meters, kilograms, seconds. We will do the same thing here. We will use kilograms, but instead of meters, we'll use kilometers. So if you want to have numbers that are like my numbers, you can use the numbers that you can do things the way that I do. So this is the speed of light in kilometers per second, and then times the number of seconds in a year. And you probably don't have that number memorized, but it's just 24 hours in a day times 3,600 seconds in an hour times 365 and a quarter days in a year, and that gives you that number. Roughly speaking, you can remember pi times 10 to the 7th if you like having rough numbers in your head. It's handy sometimes to be able to do very quick things, very quick rough answers, just to say, is that real or is that crap? And then you can get an answer real quick. And sometimes you screw up royally, but on other times people think you're smarter than you are because you can do this. So that's handy. So a light year is basically 10 to the 13 kilometers, and that's the most common unit used by astronomers because the distances between stars range from a few light years to hundreds or thousands or more light years. And in the case of distant galaxies, they may be millions of light years. Now, they also use this unit called a parsec, which is a little weird because why would you use a unit that's so similar to a light year? It's only 3.26 light years, but that's sort of for historical reasons. I'll show you what a parsec actually is. The astronomical unit is the distance from the sun to the Earth. So if you draw the sun here, and this symbol, by the way, the circle with the dot, that's the sun. We'll be using astrological symbols in here, and it's not that we really believe in astrology, but the ancient peoples produced symbols which are good shorthands for the various bodies in the solar system. And there's symbols for the zodiac too, which we don't use very much. Aquarius and Pisces and all those. And there's a couple that we use, but since we don't care much about constellations, you won't see those. And by the way, I will say something real quick about astrology. When somebody says that they're born in Pisces, what that actually means is Pisces is the time of year when the constellation Pisces, if you go from the Earth to the sun, and look at the constellation Pisces, then they're in a line with each other. So if you can't see Pisces because it's there in daytime, it's on the other side of the sun. But that's what it means. The Pisces time of the year is the time when the sun is in Pisces. Now, the problem with that is that was all figured out 1,500 years ago or something, and the equinoxes have all changed because the direction of Earth's axis has changed. So it's all different now. So the time when the Pisces, the time that's called Pisces is actually the time when the sun is in Aries or something. So even if astrology were right, it would be wrong, if you know what I mean. So okay, if let's take Earth here, and the symbol for Earth is just a circle with a plus through it. And if we take Earth's orbit around the sun, and that's intended to be something that's almost a circle, it's just my lousy math here. So the distance here, the radius of the circle is 1 astronomical unit. Now, if you go out to some very distant, the scale of course isn't right here, but if you go out some distant place, and if the line from the sun to this place is like this, the line from the Earth to that place is going to be at a slightly different angle. And so what that means is if you observe that distant place from the Earth, and then you do the same thing 6 months later, you'll see it at a slightly different place in the sky, well, say 6 months earlier. And by the way, one of the things you have to know about the solar system is basically everything in the solar system rotates counterclockwise as you see it from above. So the Earth rotates counterclockwise as seen from above. The Earth moves around the sun counterclockwise. All the planets move around counterclockwise. The moon rotates around the Earth basically counterclockwise. It's not quite lined up. The Earth is not quite lined up either because the axis isn't like this. It's actually tilted a little bit, 23.5 degrees. That's the tropical tilt. We'll talk about that later. Now, so here we are on Earth. We look out with a telescope at that distant thing, and we see it at that angle. 6 months later, or I'm sorry, 3 months later, which is a quarter of the year, we look at it again. Now, because we're displaced by 1 astronomical unit, the angle is slightly different. And if this angle is 1 second of arc, you remember what a second is. It's a 60th of a minute, which is a 60th of a degree. So 1/3600th of a degree, then this distance is 1 parsec. That's the definition of parsec. And it just happens, it's sort of a coincidence that it happens to be close to a light year. So I won't have too much to say about light years or parsecs just because we don't have occasion to get that far. We don't have the propulsion for it. If we, basically the propulsion we have, we can change the speed of something by maybe tens at the most of kilometers per second. And those turn out to be the kind of characteristic speeds in the solar system. So one of the things which it's easy to figure out is just through basic centrifugal force and high school math, you don't have to know anything. The Earth moves in a circle with a period of 1 year. You can figure out how fast Earth is moving. And it turns out to be moving about 30 kilometers per second. By the way, the number I gave you earlier, I said Earth was moving like 700 miles per hour. I don't mean Earth is moving. I mean a point on Earth's surface. Like we sitting here right now are moving roughly 700 miles per hour west to east. Well, the reason for that is just simply Earth's rotation, because Earth rotates once on its axis in 24 hours, which is a day. And actually sidereal versus solar is a small correction, but don't worry about that now. The circumference of the Earth is 25,000 miles, so 25,000 miles in 24 hours is basically 1,000 miles per hour. So west to east, you move 1,000 miles per hour. Well, I didn't say 1,000, I said 700. Well, we're not on the equator. The equator is moving west to east at this, because the circumference of the equator is 25,000 miles. The circumference where we are is smaller. It's 25,000 miles times the cosine of our latitude, which is 34 degrees. So I forget what the cosine of 34 degrees is, but anyway, it's less than 1, obviously. So you take that cosine and you multiply by the circumference of the Earth, and that's the circumference of the line of latitude that we're on, the line of latitude at Los Angeles. And so the circumference of that's how far we move in 24 hours. So that's how fast we move west to east. But now I'm talking about here in this picture, I'm talking about the motion of the Earth in its motion around the sun, and in 365 days, it moves 2 pi times 1 astronomical unit. And I did give the actual number, didn't I? I thought I did. Oh, you know what? Oh, yeah, there it is. Yeah, 1.496 times 10 to the 8 kilometers. By the way, there's a few numbers in this class. Earth's radius, an astronomical unit, the strength of the gravitational effect, the so-called gravitational parameter for Earth and for the Sun. There's like 4 or 5 or 6 numbers that it's worth memorizing. I will not force you to memorize them. When I have them on the test, I will give them to you as on a sheet with equations and constants. So I'm not going to make you memorize stuff. It will be handier if you're not always, these kinds of numbers you'll be using so many times. It's handy to commit them to memory. But again, I'm not forcing you. Okay. Let me just skip ahead to, I have a coordinate axis, right? You've seen these a million times. Now, I've oriented this in a slightly unusual way with respect to, your typical high school math textbook. So this is a 3D picture, and the way you can tell that it's 3D, well, first of all, it's shaded nicely. This is done in BTK. But notice we have these sort of cone-looking things. So from the shading of these cones, you can tell that all 3 of these cones sort of point toward us because we can't see the backward facing of the cone. So the way the orientation here, the x-axis is kind of coming out toward us, the y-axis is coming out toward us that way, z-axis basically vertical but kind of tilted a little bit toward us. So basically we're looking at this coordinate system kind of down from an oblique direction. And this is going to be typical for the way we work with Earth stuff, for example. So we're going to have, if I draw an Earth in here, then this z-axis is going to be this is going to be Earth's spin axis. Okay. And the x and the y, they will be on the equator. So the x and the y means it's the equatorial plane, the plane of Earth's equator. But more specifically, what it will mean depends on whether it's an inertial or body fixed. And we will use both of these. Inertial means that no matter how Earth rotates underneath it, x and y always point in the same fixed direction in space. Body fixed means that x and y rotate with Earth. So for example, x in that case would be typically the prime meridian, longitude equals 0. The meridian that goes north to south through Great Britain. Because they figured all this stuff out, so they got to have the longitude and they got to have the meridian go right through where they are. If the French are a little bit upset that they didn't have it go through Paris, they would have preferred that, but they didn't work it out first, so it goes through Britain and not through Paris. So we would typically express a location as being some distance along x, some distance along y, some distance along z. Now, notice, by the way, that if it's body fixed or inertial, that affects x and y, but it doesn't affect z. Why? Because if Earth is spinning, well, that's Earth's spin axis. So the z-axis, whether it's spinning or not, it's still the same direction. But if x is moving with the Earth, then it's actually rotating around like that as Earth rotates. Whereas if it's inertial, it keeps pointing in this direction, regardless of how Earth turns underneath it. So the only difference between Earth-centered and inertial and Earth-centered body fixed is the x and y axes. If it's body fixed, they rotate with the Earth. If they're inertial, they don't. They just sit there. And so the only thing you need to do to change from one set of coordinates to another is do a rotation about z. Well, we'll see how to do that later on. Not today. And how far do we have to rotate? Well, it depends on what time of day it is, because the time of day tells you where Earth is rotated with respect to this vernal equinox vector. Well, the time of day and the time of year, actually. So I'll show you how to do all that. Okay, so we have several flavors. By the way, I'm not going to trick you with left-handed coordinates. We're always going to use right-handed coordinates. So notice we had x over here crossed into y gives you z. If it was left-handed, it would be the other way around. We would have y cross x equals z. So I think the notation is pretty standard. A circumflex or a hat means a unit vector, a vector of length 1. Right? So heliocentric, helio means the sun. So we could be working, for interplanetary stuff, we're going to typically be working with axes where the origin is at the center of the sun. If it's geocentric, that means the center of the Earth. Inertial versus body fixed, that will typically be if we're working with geocentric. So if it's heliocentric, it's almost always going to be inertial. We don't typically have axes that rotate with the sun. It's not useful for anything. But on the other hand, if we're using Earth axes, then body fixed is quite useful because, among other things, coordinates on the Earth's surface are constant. If we tried to express the latitude and longitude of Los Angeles, let's say, in body fixed coordinates, we have 34 degrees north, we have 118 degrees west, and that just stays the same, right? If we had to express longitude, where we were east and west, if it were an inertial, we'd have to say what time of day it was. Oh, well, we were at 90 degrees east at 10 o'clock yesterday morning. Okay, stupid. Okay, but if we're mapping the Earth, we want the locations with respect to Earth to be fixed. So that's when we would use body fixed coordinates. Similarly, if we're trying to draw a spacecraft ground track, I don't know if you've seen pictures of this. If we want to look at a spacecraft orbit, we can look at Earth and we can look at the spacecraft moving, you know, what it actually looks like, or we can look at the spacecraft kind of projected on the map of the Earth. Where is the spacecraft? It's going over North America. Later on, it comes back up. You know, it goes over Russia or something. Okay, that's a ground track. And the way we compute that is to figure out where it is in inertial space, and then we transform that to body fixed, and we plot it on an Earth map. So we'll do all that. Okay, so you may not have memorized which is latitude and which is longitude, and in fact, some people don't get it quite straight even after they've been through this whole class. So here's the same x, y, and z. So z is north, if this is the Earth. This is the equator, and there's a prime meridian, which is the meridian for which longitude equals 0, and the body fixed x-axis is going to go through that location on the equator at longitude equals 0. So the longitude lines are north-south lines that go from the South Pole up to the North Pole, and if you take the other half of that circle, that's longitude equals 180 degrees on the other side of the Earth. Now, so this is a line of longitude, and they go north-south. And now so if we're at an east longitude, so for example, this is maybe 80 degrees or something, 70 degrees. I'm just eyeballing east longitude, which means we go in the easterly direction. You remember how west and east goes on Earth maps. If west is to the left, east is to the right, north is up, and south is down. So we go off to the east some distance, and then we're now at some eastern longitude, and then the latitude is how far north we are of the equator. So if we have some point on the Earth's surface, we look how far east we are, and we look how far north we are, and that's longitude and latitude. Now, there's some consequences of this. If you think about this, then say I draw a picture from the side. So here's north, here's the equator. I'm going to draw some lines of latitude, and notice they get shorter as you go toward the poles. So if I draw a couple of lines of longitude, the lines of longitude converge at the poles. So if I were to go, say, 1 degree eastward in longitude, then how far that actually is in miles or kilometers, that depends on where we are on the Earth's surface. Okay, if on the equator, if I go 1 degree east, that may be a long way. But if I'm standing 10 feet from the North Pole, 1 degree east may be an inch or something, you know, or I didn't figure it out. Actually, it probably is an order an inch. So longitude, how far a unit of longitude is latitude dependent, because all the lines of longitude come together at the poles. On the other hand, the lines of latitude, the angle, or the distance rather, is always expressed as the same fraction of the Earth's surface. So 1 degree of latitude is always the same amount. So if I'm on the North Pole and I say, okay, I'm going to go 1 degree south, then I have to walk some distance, whatever that distance is. I kind of recall it's like 60 miles, something like that. 60 miles to get there. Actually, it's easy to figure that out because you just take the circumference of the Earth and divide 360 into it, and whatever that comes to be, that's how far a degree is in latitude. So if I'm at the equator and I walk 1 degree south, that distance is the same. By the way, one of the puzzles they like to give you in elementary school is, have you guys heard this one? Where is it on the Earth's surface that you can walk a mile south and then a mile east and then a mile north and you come back at the same place? Do you guys know the answer to that?
North Pole or Pole?
North Pole. North Pole is correct because you go south and then east, and then you're still a mile south of the North Pole. So if you go back north again, you're at the same place. That's not the only place, though, as it turns out. There's other places too for which that's true. So, just for example, say you're down here, sort of near the South Pole, and suppose you walk south. That takes you down to here. Now, suppose you're close enough to the South Pole that a line of latitude is a mile long. Well, as you get close to the pole, the lines of latitude get very, very short. If you're 1 foot from the North Pole or the South Pole, the line of latitude right there is 2 pi feet around, right? So the lines of latitude get real short. So if you're down here and if you go a mile south and then you go a mile east and you happen to now be at the latitude for which it's 1 mile around, now you're at the same place. You go back north again, you're here. See? More solutions, and they don't tell you those. So, well, we're not done yet. Okay? In fact, if we go closer to the South Pole, there's a line of latitude where the circumference is a half a mile, right? So if you were on that latitude and you went a mile east, you'd go twice around the Earth, back at the same place. Mile north, you're there again. So you see there's an infinite number of latitudes at which that's true. So this is sort of a metaphor for both engineering and science, actually, because the quick thinking person, and this might be you doing homework, you know what I'm saying? Somebody asks a question on the homework and you go, oh, you write it down, done, off to the pizza shop. But actually, there are multiple solutions, and the one you missed is actually the real one for some key reason. You know what I mean? That can and will happen. So it often happens when you're thinking of how to actually do something, whether it's in some physical place like the rocket lab or whether you're trying to do this in mathematical space or something. You're trying to do something, and you see how to do it. You may just kind of jump at it and do it. Maybe it works. A lot of times it will. But more often, if you think about it harder, there turn out to be a bunch of different ways to do it, and some may be deeply better, some may be deeply worse. But the point is, you're not going to find them unless you actually sit and think about it for a while. So it sometimes happens that people that you think of as being kind of stupid because they don't talk real quick, you know, and you ask them a question and kind of nothing happens for a while and then they answer, and you think they're stupid. But what actually happens is they're thinking a lot. And when they give you an answer, it may have all this kind of digesting going on, and they may, well, it could be like this or this or this, and they give you 10 different answers, and here's what's good about this one, here's bad about that one. So these deep thinkers, they're important people too. And so if you just talk to people and make an assessment of how smart they are based on how quick or sharp or any of those kind of things, you may get the wrong answer. So, and by the way, I was kind of conceited in my youth because, you know, I was smart in school and all that, and I could read and do all these things better than my more athletic peers as kids. And so I thought, oh boy, I'm smart, you know. And so when I got up in my early career, I thought, well, you know, brains are the most important thing. But after a while, I realized actually that's not really true. And I first got an inkling of it when I'd been teaching for a few years, and some guys got out of school, and, you know, I'd run into them a few years later, and they get a hold of me, and they send me an email, or I run into them somewhere, and I ask what they're up to, and oh, I'm a vice president at Rockwell or something, and wait a minute, weren't you? Yeah, that's right. They kind of smile woefully and say, yeah, I was a C student. Well, the stuff you do in classes it's fine to get good grades, other things being equal, 4.0, yeah, that's great, but that doesn't correlate with how well you're going to actually do. And the kind of people that are actually worth something, they have a whole different set of qualities. It's got nothing to do with the GPA. So after a bunch of things like that happened, after a while I realized I don't know anything about how people are going to succeed. And actually, it isn't just me. I mean, yeah, I was kind of stupid, but all of industry doesn't know how people are going to succeed. You can tell because what's actually true in companies is when you have a big group of people, like if you go to Microsoft and find the group that's working on the next Windows or something, that may be 8,000 people. Well, in that group, of those, maybe a few hundred are going to be the productive people, the people that really do important stuff. The other people, they're kind of looking around for things so that they won't get in the way. So the simple rule is the 80-20 rule, and those numbers change around a little bit, but 80% of the work is done by 20% of the people, and nobody knows who the good 20% are going to be. And so GPA correlates with it a little bit. So companies in grad schools, they try to hire people with good GPAs. Grad schools more because they tend to select for people who are going to be professors, and professors like to give grades to people like them. You know what I mean? So it's all it's all sort of a rigged system. But as far as if you're going to succeed in industry or starting your own company or something, that's a whole different set of skills. And companies don't know how to find those skills, so they hire you, and maybe you do well, maybe you don't. And in the last few years, they've gotten smarter about that. They figure, okay, if you come and work for us over a couple summers, now we know how good you are. And that's a way better indicator. So most of you guys are going to do some kind of summer internships, and for a lot of you, that's going to actually lead to permanent positions because they see how you are and they like you and you like them if you get lucky and land in a good group. Don't think you have to do that, though. If they like you at some summer internship, it doesn't mean you have to like them back. Right? It's a big world. You can shop around. You're good guys. So I do a lot of digressions. You may have observed. Right. Okay, so that is latitude and longitude, and I will give a little later on formulas for how to convert positions to latitude and longitude. Okay. Are we? Ooh. All right. One thing more, and I will show you something really quick, and then we're out of here. I have one more minute. Okay, I alluded to the fact that the Earth's north axis is tilted, and this is going to turn out to be pretty important, particularly when we do interplanetary kind of stuff. So there's the plane where all the planets are, the so-called ecliptic plane, the plane of Earth's orbit around the sun. And there's the plane with Earth's equator, the so-called equatorial plane. And those aren't the same. There's an angle between the two, and it's 23.5 degrees, which coincidentally is the latitude of the Tropic of Cancer and Capricorn. It's not a coincidence. It's the same number. Okay, so this is what gives rise to the seasons. I'll show you all this stuff. But if you have two planes, they intersect along a line, and these planes are constant in time because the equatorial plane doesn't move, the ecliptic plane doesn't move. So the line joining them, or the line common to both, doesn't move either. This is a way that we can get an inertial direction. So in fact, this is where we get our inertial x-axis. This is a direction that it's common to both Earth-centered stuff and Sun-centered, and it's fixed in time and space. So, in direction. So this is how we get an inertial direction. So we will pick this up on Thursday, and I'm going to sit here and futz with my machine and see if I can't sort out my pen and stuff. So if any of you registered late, you won't have got email from me. So please send me email. And then I'll know who you are, and I'll add you to the class list. Otherwise, I'll see you on Thursday. Hi.
I have a question.
Okay. Video is ending now.